CERN's Large Hadron Collider may have uncovered the first proof of something monumental. It's been over a decade since the Higgs boson stunned the world and put CERN's Large Hadron Collider, LHC, on the map as the crown jewel of modern science. Back then, the discovery was celebrated like a moon landing, a confirmation of a 50-year-old theory and a triumph of human curiosity. But fast forward to 2025, and something just as powerful, though quieter, is happening beneath the Swiss-French border. The LHC hasn't found another God particle, but what it has done this year may ultimately be even more transformative. It's reshaping our understanding of the universe, one collision at a time. Struggling to understand what's next after the Higgs? You're not alone. For years, many asked, what's left for the LHC to do? Once the Higgs was discovered, wasn't the biggest mystery solved? The short answer, not even close. The Standard Model, the theory that explains how particles and forces interact, is astonishingly successful, but it's also frustratingly incomplete. It can't explain dark matter, gravity, or why the universe favors matter over antimatter. It's like finishing a puzzle and realizing the most important pieces are missing. Enter 2025, the year the LHC took that puzzle, flipped it upside down, and started looking underneath the table. The Breakthrough Prize, a Nobel-level nod to quiet genius. This year, the four main LHC experiments, AL, ICE, ATLAS, CMS, and LHCb, were awarded the Breakthrough Prize in Fundamental Physics. Think of it as the Oscars of science, but with a lot more math. What did they win for? Higgs precision. They didn't just find the Higgs. They've spent years measuring it with surgical accuracy, confirming how particles get mass via the Brout-Englert-Higgs mechanism. A new particle zoo. Over 72 new hadrons, complex particles made of quarks, have been discovered, many unlike anything seen before. Deep dive into antimatter. The LHCb experiment continues to uncover the mysterious imbalance between matter and antimatter through CP violation studies. Recreating the Big Bang. ALICE is simulating the earliest state of matter, quark-gluon plasma, to understand how the universe was born. The frontier of the unknown. Even without confirming new physics yet, experiments are setting powerful constraints on supersymmetry, dark matter, and extra dimensions. This isn't one eureka moment. It's a symphony of small revolutions, each one nudging the door of understanding a little further open. Let's talk numbers. What the LHC is doing in 2025. The collider is humming at a jaw-dropping 13.6 tera-electron volts, the highest energy ever used for particle smashing. And for the first time ever, the LHC is using oxygen ions, adding a new dimension to its already ambitious physics campaign. Every run, every collision, every new measurement in 2025 is another attempt to peer into the fabric of existence itself. And what they're finding is extraordinary. The Higgs isn't just real, it's precise. Multiple decay channels, cross-sections, and coupling constants are now being measured to confirm the Standard Model and search for signs of new physics hiding in the margins. Hadrons galore. Some of the new particles discovered, like tetraquarks and pentaquarks, were only theoretical dreams until now. These discoveries deepen our knowledge of quantum chromodynamics, the force that binds the nucleus together. CP violation clues. Why does anything exist at all? LHCb's data on matter-antimatter asymmetry is part of that answer. The tiniest imbalance in particle decay is a cosmic clue. Hotter than the Big Bang, Alice is achieving temperatures over 5 trillion degrees, briefly recreating the primordial soup that existed milliseconds after the Big Bang. New physics? Not yet, but closer than ever. Susie and dark matter might still be elusive, but every non-result is narrowing the field and guiding future discovery. Even the world's best minds are watching closely. Nobel laureates, university labs, and theorists around the globe are hanging on every result. "We're at the threshold of something big," said one physicist involved in the CMS collaboration. "It's not about finding a new particle anymore. It's about understanding why there isn't one yet." The Breakthrough Prize Committee praised CERN scientists for delivering a deeper understanding of the quantum world through patience, collaboration, and clarity. And public interest is growing again. With media coverage and outreach campaigns, even casual science lovers are tuning back in, because this story isn't over. In 2030, CERN will launch the High Luminosity LHC. It's more than an upgrade, it's a scientific revolution. By collecting 10 times more data, it will allow researchers to observe extremely rare particle events, measure the Higgs boson's self-interaction, and perhaps finally unlock physics beyond the standard model. It's the next step in a story that started with atoms, exploded with quarks, and now unfolds at the edge of time and energy. And you're living through it. The beauty baryon that broke the rules. In a landmark discovery, scientists at CERN's LHCb experiment observed CP violation in the decays of beauty lambda baryons. This is a first, and it changes everything. Let's break that down. Beauty lambda baryons are particles made of 3 quarks, just like protons and neutrons, but with one of those quarks being a heavy beauty or bottom quark. CP violation refers to charge parity violation, a phenomenon where particles and their antimatter twins don't behave in mirror image ways. This behavior directly violates one of the universe's assumed symmetries, suggesting a possible reason matter survived while antimatter vanished. And here's the kicker. The result passed the gold standard of discovery in physics, a 5.2 sigma significance. That's less than a 1 in 3.5 million chance it was a fluke. In layman's terms, we just watched the universe cheat, and that cheat may be why you're alive. Struggling with the question, why does anything exist? If that question keeps you up at night, you're not alone. For physicists, philosophers, and thinkers of every stripe, the imbalance between matter and antimatter is one of the deepest mysteries in science. Until now, all confirmed CP violations had been seen only in mesons, particles made of quark-antiquark pairs. But baryons, the building blocks of matter, like protons and neutrons, had never been caught breaking this symmetry. Not until this year. This new discovery shows that baryons also misbehave. And that matters, because it brings us one step closer to understanding how the early universe made its choice to favor matter not antimatter, and that changes everything. A quantum shift in the Standard Model. This isn't just a cool data point. It's a crack in the Standard Model, the tried and tested framework physicists have used for decades to understand particles and forces. The Standard Model doesn't adequately explain why matter dominates. CP violation is built into it, but not enough to create the universe we see today. It's like knowing someone cheated in a race, but they're still too slow to have won. So now, with baryons violating CP symmetry, we have new physics to chase, new theories to build, new experiments to run. This is what scientists mean by a quantum shift, not just a small tweak, but a possible rewrite of the rules. Emotion meets equation. The stakes are cosmic. This isn't just about particles colliding. It's about why the stars exist, why Earth formed, why you're reading this sentence instead of being a wisp of light lost in a void. Imagine the early universe as a battlefield of opposites, matter and antimatter, locked in a furious balance. This discovery suggests matter might have had a secret weapon, a subtle bias embedded in the laws of physics that tipped the scales just enough to win. If you've ever felt insignificant in the cosmos, think again. This imbalance made your existence possible, and now we may finally understand how. The LHC in 2025, a season of firsts. The CP violation discovery wasn't the only headline from CERN this year. The LHC also kicked off the 2025 physics season with 13.6 tera-electron-volt proton collisions, the highest energies ever reached in controlled experiments. Scheduled its first oxygen ion run for July, aiming to probe nuclear matter under extreme conditions. Saw its 4 major collaborations, ALICE, ATLAS, CMS, and LHCb, win the prestigious 2025 Breakthrough Prize in Fundamental Physics, celebrating their collective contributions to our understanding of the universe. This isn't just a lab, it's a symphony of science, and it's playing louder than ever. This is the beginning of the next physics revolution. The next steps? More data. LHC's Run 3 is ongoing, and with more collisions, the statistical power of these findings will grow. Theoretical expansion. New physics models, maybe even hints of supersymmetry or quantum gravity, may rise to explain this anomaly. Technological ripples. As always, breakthroughs in particle physics tend to leak into the real world, giving us new tools from medical imaging to encryption systems. But most importantly, this sets the tone for the next generation of physicists, those inspired by today's mysteries to become tomorrow's explorers. Maybe that's you. Maybe it's your child. Maybe it's someone reading this who's just now realizing the universe has secrets waiting to be uncovered. You've witnessed a moment of creation. Now, be part of it. This isn't fiction. It's not a movie. It's not some abstract idea floating in a lab in Switzerland. This is the real story of how we came to be. And in 2025, we took a giant step closer to understanding it. The Large Hadron Collider showed us something no one had ever seen. It proved that even at the smallest scale, struggling with old models, that can't explain new realities, you're not alone. Physicists have wrestled with this for decades. The Standard Model has been stunningly accurate, but incomplete. It can't explain dark matter, most of the universe, dark energy, what's making the universe expand faster, gravity, yes, even that, or the matter-antimatter imbalance. This new discovery shines a spotlight on that last one. By showing CP violation in baryons, we now have a new path forward, a new place to dig for answers. And the digging is just beginning. Even the experts are fired up. Let's hear it from the inside. The more systems in which we observe CP violations and the more precise the measurements are, the more opportunities we have to test the Standard Model and to look for physics beyond it. The first ever observation of CP violation in a baryon decay paves the way for further theoretical and experimental investigations. Vagnoni, LHCb spokesperson. This isn't hype. This is history. When scientists at the most powerful particle collider in the world start talking like this, you listen. No, it's not the end, but it's definitely the beginning. Some headlines screamed, "End of the Standard Model." That's misleading. Here's what actually happened. The Standard Model predicted CP violation in baryons, so this confirms it. But the amount of CP violation still falls short of explaining our universe. Therefore, the Standard Model still works, but not fully. That's why this discovery doesn't break the model. It points beyond it. It's like finding the edge of a treasure map. You don't throw the map away, you follow it further. This is more than physics. It's a mirror of the human spirit. You've questioned the rules before. You've wondered what lies beyond the known. This moment is proof that even the smartest minds in the world still ask why. And sometimes they find answers. If you've ever seen yourself as a rebel, a thinker, a seeker, then welcome, because what CERN just uncovered is your invitation to think bigger. The path ahead, a new era of discovery. So, what's next? More experiments. At CERN, scientists will now test other baryons. Do they show similar CP violations? New theoretical models. Physicists are already sketching out extensions to the Standard Model that could account for these anomalies. Next-gen colliders. Plans for even more powerful machines like the Future Circular Collider are gaining momentum. Bigger machines mean deeper insight. We are entering a new age of physics, a time when bold ideas and precise data will shape the future. You've witnessed the spark. Now, help light the fire. You've just traveled into the heart of matter, into a place where quarks dance, symmetry breaks, and the future of science is written in particle trails. You're not just a reader. You're a participant in one of the most profound revolutions in human understanding. Because every time the universe gives up one of its secrets, it doesn't just change textbooks, it changes us. So here's your moment. Ask questions, stay curious, support science, share this story. Teach someone about CP violation. Follow the next breakthrough. Because the Standard Model isn't dead, it's evolving. And with this discovery, so are we.